The list of vision language models available today is ever expanding. Seemingly every week, every 2 weeks, there's a new model that comes out, whether by an existing provider or a new open source one too. And over the past few months, we've seen everything from new Claudes to new Geminis to new GPTs to the kind of increased interest in reasoning models and launches thereof. We've seen open source get better with Quens and Llamas. And with all of these vision language models that, given an image, can answer a question, I have a question. How do I find the right model for my use case? And this isn't something I can just go ask a vision language model. So let's talk about comparing vision language models on real world tasks in manufacturing environments and retail environments on tasks where we want as accurate an answer as possible. Consider this example here, where on the left there's an image of a vending machine area with various different consumer packaged goods. We may have a question about this retail environment, like how many empty spaces are on the bottom shelf? And we could ask that for all the shelves here. We could even do planogram adherence. The correct answer to this question is three, but how do I find the model that's going to return that correct answer? Ideally, we would have a report like this that says, okay, Claude and Gemini both get this right. They're good for this use case. And these other models don't answer the specific question. Um, in our test of this very image and this very prompt against over 15 state-of-the-art language models, only 2 out of 19 got this specific question correct. And so that leads us into the topic of today's webinar. I'm James, and today I'll be chatting about how to find the best VLM for your use case. So the first question is, what is a VLM? So VLMs are vision language models. They're language models that are capable of answering questions about the contents of either one image or indeed multiple images, and in some cases, even videos. On the right here, we've got a few examples of prompts that you could ask a language model. Is there scratch on metal? What's a row state on a label? When does a chart start to asymptotes? How many boxes are missing on a pallet of boxes? Really, if you have a question and an image, you can ask it to a vision language model. Vision language models are trained on huge data sets, think hundreds of millions, billions of images, and also can be fine-tuned for better performance on specific tasks too. And so some of the headliners I mentioned earlier, like the GPT series, the O1 reasoning series, both from OpenAI and Gemini and such, all examples of vision-capable language models. But this question of how do you find the right VLM for your use case is kind of tricky, and we're still figuring it out. VLMs can do a lot, but the line between what they can do easily, what they struggle with, and what they're kind of unsure about is often unintuitive. One state-of-the-art kind of means by which we evaluate the progress in these models is, as is the case in many other domains of computing, benchmarks. In the case of language models and computer vision, we have benchmarks that have a question, the ground truth answer, and then we compare the result from the model against that ground truth. Now, these benchmarks can be huge and can be focused on more abstract concepts. So on the right here, we see GPT 4.5 evaluation scores from OpenAI's model release blog post. And in it, we can see there's a benchmark for science, for math, for two for coding, one for multimodal reasoning and question answering, MMMU, one for multilingual. And reading this, there's one, a lot of acronyms, and two, there's the question of, well, how does a VLM do on my specific use case? The benchmarks, while useful, are often huge. They're somewhat intractable as a result and don't ground you in your specific use case. On the other kind of end of the spectrum, there are hand-picked assessments. Go into a large language model, ask a question, get a response. But doing that is time-consuming, particularly when you're evaluating against maybe a dozen cloud models, a couple open source models. It takes time to do all of that, kind of those comparisons, and that time only increases with the number of prompts you want to run. That leads me to another question. What if there was a visual way to see how these state-of-the-art VLMs do on a range of tasks, a range of real-world tasks, the kind of things that you may be wondering, can VLMs do this for my enterprise? Can VLMs do this for my side projects? And that's where RoboFlow's latest project, Vision AI Checkup, comes in. So Vision AI Checkup is what we're calling the optometrist for VLMs. With Vision AI Checkup, you can compare how over 15 different VLMs do on a wide range of prompts, over 80 prompts. I think right now we're at 85. And every model gets its own report card, so you can see how the model does. Every prompt that's run also has its own report card, so you can see how all models do on that prompt. And then you can also see, filtered by task, which models are best for that particular use case. On the left here, you can see a sample of the leaderboard as it stands right now. And then on the right, you see one of these model cards where 4.1 Mini, presently at the top of our leaderboard, ranks number one for a range of use cases, color identification, web action understanding, OCR, and we can see some of those prompts too. But rather than talk about some images, let's do a demo and explore some of these state-of-the-art models. I am going to head to our Vision AI Checkup. This is available at visioncheckup.com. And on this site, the first thing you will see, aside from great illustrations taking us back to the optometry theme, is a leaderboard, which shows the best models run on each 5 different prompts. And as we have more, this will change and that number will increase how these models perform on those prompts. So right now at the top, we've got some of OpenAI's models in aggregate are doing the best, followed by Gemini, Llama 4, Gemma 3, and in some cases, there's kind of joint performance too. So in this case, for these three models, they're all ranked number 5. Their score is the same. And in addition to the score, which is the percentage of prompts each model gets right, we also have an average request time too. And already from this chart, we can see that O4 Mini, while being number 2, takes twice as long on average to respond to a request as 4.0, which makes sense because O4 Mini is one of their pioneering reasoning models, which are promised to take longer and think more. And then on the other side, these ones that are just slightly lower in score, like Gemini Flash, responds in 3 seconds, which is half the time of that top model. And so this already gets us to the point of, okay, these models score differently, they have different times. What are my trade-offs that I can use to kind of make a decision about which one's best? And in order to kind of do that, we have a few different things available. First is if we click this best overall, I can choose a particular domain in which I want to evaluate model performance. So let's say I'm doing a document understanding task. We've got 7 prompts that fall under that category. And here we can see that most models in our assessment do really well on this task. And if I show more of them, some of them, like 4.1 Nano, surprisingly, doesn't do very well for our document understanding questions. But honestly, if you pick like a top tier off the shelf model, it's going to do pretty good on this task. But if I go to something like, say, object counting, count the number of objects in an image, we can see this report is very different. Of 9 prompts, the best model is Claude, and it only gets the question right 50% of the time. So yeah, it's really interesting seeing this variability by task and having this leaderboard where we can kind of explore it a little bit. So let's go into one of these models. Let's take a look at O4 Mini, for example. So for Mini is among the best in aggregate. And on the report card page, we can see all the prompts that we ran through. And I'll take a look at this one, where we asked, is there a box in the background of this image? The ground truth is yes, and the model output is yes, which is great. And indeed, there is a box, in fact, 2 boxes in the background. And these prompts have all been written to be real-world tasks that you may want to ask a model about. For example, are your coffee plants ready to farm based on whether the majority of cherries are red? The model said no. The ground truth was no. And we can see here, indeed, the majority of cherries are not red. The model was correct. But if we scroll down even further, we start to get to the ones where the model doesn't do so well. And then on the left, this kind of by task view pops into the viewport. So we can see, let's look at defect detection. For example, this prompt here for defect detection on bends, we're asking the question, are there any bends in this part, yes or no? The answer is yes. The model said no. And we can see here this part is bent relative to all the others. And this was taken from a data set of defective parts in which that was identified as a defect. And scrolling down further, we really get more insights into what this model for MIDI does well and not so well. Looking at object counting, only got 3 of 9 prompts right. Defect detection, I got 10 of 17. If we click into the defect detection one, we can start again get even more insights. It did well at identifying moisture on cans, but it didn't do so well at finding a dent in this piece of metal, for example. Um, in fact, this one it actually got right, so I'll need to play around with that matching. Let's look at another one here. So, a missing part in the box. How many parts are missing? Return a number. The model said three. The actual answer is one. So again, we build this insight into how the models are doing. We can then go to the prompts overall and see all the prompts in our kind of assessment. One that has been really interesting of the 85 is this one here for glass rim detection, which will defect detection, which I'll come back to in a minute. But these kind of run the gamut of possibilities of questions, like how wide is a sticker relative to a reference object? How many bottles are in a refrigerator? What date is picked on a web-based calendar? What are the dimensions of an area on a floor plan? What's the serial number on the tire? So we're really indexing for as many different practical use cases as possible. Screws in an assembly line, in a tray, doc numbers on a receipt or a shipping manifest rather. Um, I'm going to go back to this glass rim track one. Like click into it, we can see only 2 of 90 models actually answered this question. Is the glass rim cracked? Yes or no? Correctly. If we zoom in really far, we can see two slight cracks. And this is one use case that Overflow has been used for is identifying cracks in glass rims. And we can visually see these defects, although they're faint, but only two models got this right, 4.0 and Gemma 3, which in aggregate are two of the best models on our leaderboard. But it's interesting to see that, okay, 4.1 coheres, I am a series, Claude's series of models, those don't do so well for this task. So with Vision AI Checkup, we get all these reports by model performance, by prompt performance. And one of the best parts is it's open source. So if you click the add a prompt button, you're going to be taken to GitHub where you can submit your own prompt. Add the title and image prompt. We'll put it into our assessment index and we will rerun the assessment and recompute the leaderboard. So yeah, right now those OpenAI models are doing really well and we'll see how things change over time. With that said, I'll go back to my slides. What have we learned so far? What has RoboFlow learned by looking through some of these visual results? Firstly, VLMs really struggle with object counting. Often the model's off by one, it may be off by two. In some cases where there's a large number of objects in an image, it can be off by 10 or more. And so if you're trying to do anything that involves counting objects, a VLM may not be best. We also learned generally there's massive variability between models. Some models really excel at some tasks and struggle with others. Some models are generally good across the board, but again, there are blind spots like object counting. And it comes back to a fundamental principle of software engineering and indeed the kind of nascent field of AI engineering is choosing the right model is essential and it takes time to do. So we're hoping Vision AI Checkup kind of gets you to a point where you feel more confident in model capabilities and you can use that to start be more selective in which you evaluate, knowing that these four models, for example, are better at receipt reading or reading shipping manifests or counting the number of screws on a tray. Some models, yeah, they do better than others at specific tasks. Another thing is, and we knew this already, but multimodal models are slow, and reasoning models are even slower. Like one of OpenAI's reasoning models was towards the top of our leaderboard, but it was twice as slow as another one with almost comparable performance on our tests. So that really leads us to again another part of engineering of given all the possibilities and what's the request time and response time that you need in order to develop the best possible user experience if it's an application, or indeed the best possible system if VLMs are plugging into a much larger backend. The next steps for Vision AI Checkup, this project, is we're going to add more models as they come out. Next time a new model comes out that kind of grabs headlines, we'll be adding it in here and we'll see how it stacks up on this leaderboard of real world handpicked assessments made by both RoboFlow and the community. We'll also be adding more prompts. If anyone submits an issue to the repository, we'll be adding those into the project. And then also we'll just be checking over time how these models do, how they get better, how they change. Object counting may be a blind spot now, but maybe in 6 months it won't be. Indeed, this has been the case in VLMs, where a task that a model may struggle with one day, it gets better over time with more data, with different training techniques, and as the field matures and the research available leads us to a better insights on how to improve performance on some of these tasks. Maybe object measurement might get better over time too. So we've got the link there, github.com/overflow/vision AI checkup. If you want to contribute, add a model, add a prompt, play around, it's all open source. Now, the next thing is where are VLMs going? At RoboFlow, we consider there to be two concurrent revolutions going on in vision AI right now. The first is that pre-trained LLMs, which only 2 years ago were the relatively sparse in terms of availability. We had VLMs, but I think one of the ones that really changed how we interact with them was when GPT released GPT with Vision, and you could upload that image and get a response to your question. That was kind of groundbreaking in that user experience sense of, wow, a language model can deal with vision too. But the history is much longer too. But now today, these models are getting better, they're getting more accurate, and they're able to cover more tasks. With that said, though, they're not really suitable for running in real time. As we saw, response times can be a few seconds for some of these general question answer type problem statements. And then on the other side, we've got these task-specific vision models. So we've been talking about all about VLMs, which are trying to do a lot of different things in a lot of different domains. But ultimately, a lot of the use to be found in certainly in enterprise and also for side projects too is in very specific domains where you expect the best possible performance. You want the model to confidently answer your questions correctly as many times as possible. Indeed, this is the kind of promise of computer vision more broadly, is being able to identify defects with high accuracy, being able to identify relations between objects in an image, being able to understand everything from floor plans to satellite imagery. Accuracy is essential. And for that, we often lean towards some of these task-specific vision models. It may be an object detection model to identify defects, like that tough glass rim one we saw, or it may be a segmentation model um, to do something like identify a t-shirt so you can do color analysis and make sure that the ink color is as expected. So yeah, task-specific vision models, object detection, segmentation, classification are playing a huge role. And they also run faster. You can have a object detection model on your line running at 25 frames per second easily. But the trend we're seeing is combining both of these. So imagine a world where the VLM reads a shipping manifest and puts that into a programmatically kind of parsable format. And then you have a detection model that finds all the different SKUs on, say, a pallet of goods, a pallet of boxes, and makes sure that that image of the pallet lines up to the shipping manifest. Neither of those are possible, VLMs or object detection, for example, alone, but together you're able to do that. And so VLMs and task-specific models only add to our ability of building visual intelligence that plugs into the enterprise and solves these real-world problems that we have today. Here. So the image isn't loading here, but I will go. Oh, here we go. So one insight I did want to talk about is this is an example of a glass defect detection model. If I go in here, this is in RoboFlow. I have this model that's trained on over 1,000 different images of glass with defects. And there's a tiny little scratch here, a tiny little visual blemish, and our model is able to detect that. And it also gets the glass too, whereas that multimodal model struggled. This model can run in real time, which shows again these two concurrent revolutions of models being able to do different things well, and you as kind of a builder having kind of seen all of this, can now start to make decisions about, okay, what tool is best for my use case? And from this image alone, we can get a lot of information. We can see the presence or absence of defects. We get real-time insights on when defects are found, number of glasses or defects present, and so many more insights. And because it runs in real time, this can connect directly to a manufacturing system and help empower decisions. You could if the defect rate of, say, scratches in glass increases over a certain threshold, have an operator investigate in real time with a kind of fine-tuned detection model. Might go back here. And go to the next slide. On the topic of combining VLMs and detection models, when you combine the two, you get kind of greater than the sum of its parts in a way. You could build a workflow that identifies products and image, it crops all the labels, it sends those labels to a multimodal model for OCR, which we previously established is a really good task at which many of the state-of-the-art models are really good, and then returns the contents of each label. And to do this, the one thing you can do is use RibbleFlow workflows. So on the right here, we've got a workflow that's using YOLO World, an open source object detection model that has object grounding. So I can say, find me a label, and it will find the labels. Then we crop all the labels. We send it to a multimodal model for kind of OCR and information extraction. And then we come back and get an output. So I actually built this workflow and I'll show it here. I made this a little while ago. I love coffee. And I was curious, like given an image of a bag of coffee like this one, could I extract different pieces of information? So I built this workflow that uses YOLO World to find the coffee packaging. So this could have 10 different packages in the image, and it's going to crop out each individual one, process them with a multimodal model, and then return a result that correlates the information extracted to the exact image of the package, which is great in any enterprise scenario where you have multiple objects and you care about that visual versus rounded data correlation and saving that as a record, say, in a database. And then my prompt to OpenAI is read the tasting notes and returns a comma separated list, that classic natural language visual question answering kind of form. And then in my test here, if I go to the visual output, you can see our object detection model got the coffee packaging, this purple box here. It cropped that out, sent it to a multimodal model, and then our output from that is chocolate, caramel, and citrus, the tasting notes, which are present here on the coffee bag. So that is to say, we combined the two and we got we got the response we're looking for. We were able to derive real world insights. And with that said, thank you very much. You can join us next time at ribbleflow.com/webinar.